All right, and I am pleased to introduce Matt Mathis from Google, and Matt's going to be talking about the Bbr TCP project. We're going to be doing it a little bit differently today. I'm going to be showing the slides, and Eli Dart has agreed to sort of monitor the chat room for questions as they come in. So let me share my screen. And hopefully you can see that, Matt.
Yep, I can see exactly where you are, and I have my own copy.
Okay.
This is a new experience for me. Hello and good afternoon, everybody. The Zoom stuff doesn't run on the machines we have at work, so I'm actually doing this from my kitchen, but I think that will work just fine. I'm giving a talk today, which is basically recycled slides from other talks given by other people, pulled together from my own point of view. Many of you know me from nearly 30 years at Pittsburgh Supercomputing Center, at Carnegie Mellon and Pittsburgh Supercomputing Center, doing internet performance stuff. And this is the piece that I was looking for but didn't find, and Van Jacobson and others found it after I went on to do other things at Google. So I will be talking about work of other people that is very dear to my heart, but I didn't actually do the work. Next slide, please. Okay, so the outline today, I'm going to first of all do a kind of a quick overview of some of the things that go wrong with loss-based congestion control. Probably everybody here is very familiar with one of the aspects, but it turns out there's a bunch of other ones that are more of a problem in the commercial internet. I'm going to introduce BBR and talk about how it works and give sort of cartoonish examples of how it behaves, and then talk about some results in the field, not a real lot of detail, and then go on to talk about future work and where we see more things that need to be done. Next slide. So this is Google's perspective on where the problems are, but in fact, in the HPC community, the excessive sensitivity to packet loss has been a known problem for easily 15 years and maybe 20 years before this. That congestion control that is triggered by single packet losses at high data rates and large windows has been a major problem in the HPC community. It boils down to packet loss is just not a good signal for congestion. There's a bunch of things that are wrong with it. Next slide, please. The way to think about this is you have this these curves which give you the delivery rate and round trip time as functions of window size. What Reno and Tahoe and Cubic all do is control against the onset of losses. As certain people in the community like to say, the control to the edge of the cliff rather than the knee. And this is a problem in cases that are overbuffered, which is typically what happens in low-speed edges of the network for the users, for customers. Next slide. And in the HPC environment, we see sort of the opposite problem. We get underutilization because the losses are too high and the required signal noise ratio is too low. Next slide, please. It was proven by Kleinrock the optimal point to be is at the knee, and it was also proven that there's no distributed city cell algorithms to find this point. This was sort of the setting of the state of congestion control. Well, I didn't understand the theoretical results when I first started looking at performance, that it was already known that there were not good distributed algorithms to do certain things. So next slide. How does BBR deal with this? Well, BBR stands for bottleneck bandwidth and round trip propagation measurement. It's a complete redesign of congestion control. It went back to first principles. When Van first came to Google, I had a conversation with him about, I spent my first couple of years at Google redoing the past 20 years of my career at some level. And you should consider the same thing. And he took my words to heart. And he went back and basically rethought all the stuff, all the thoughts that went into VAN 88. So BBR tries to directly measure the bottleneck bandwidth and the minimum round trip time and use that to drive a model of the network. And the key insight that was missed from the earlier theoretical work is that the result depended on the assertion that you couldn't find a steady state measurement that got both the round trip time and the max bandwidth and the minimum round trip time correctly. But in fact, the network itself is fairly stationary, and the insight that led into BBR is that you can actually do them sequentially. You don't need to do them at the same time. Next slide. So here are those same two curves again, and as the operating point bounces around, you either get to observe the minimum RTT or the maximum bandwidth. You don't ever simultaneously, well, unless you happen to get lucky, you don't necessarily see both of them, but you can get lots of data for either one. Next slide, please. So as you bounce around and hit various different operating points, you will capture an observation of the minimum round trip time and the maximum RTT. And that's sort of the key insight, finding that operating point, and the key thing that BBR does differently. So next slide. So here's the core design. There's a fairly complicated state machine that is carried in essentially the retransmit scoreboard. It keeps a lot of statistics. Every single ACK turns into a data point measuring measuring both the bandwidth and the RTT relative to the packet that triggered that ACK. And then you use these ACKs to update the estimate of the maximum bandwidth and the minimum RTT. Of course, many of them are not max or min as appropriate, but you throw them away. And you keep these two filters, which have actually precisely carefully engineered numbers of how long you keep the max and min. And the max bandwidth and min RTT gives you a fairly precise estimate of exactly where that operating point is. So the control sequence is to mostly run at the optimal data rate, but once in a while, bop up and down to make sure that you probe for both the minimum RTT and the maximum bandwidth. The details of that probing has actually been subject of a lot of the work that appears in the code and sort of in the discussion in the emails and various threads about evaluating the algorithm. But it doesn't appear in the core algorithm. The core algorithm hasn't changed at all for a long time. There's a secondary control, which is to prevent is necessary to stabilize the behavior in a bunch of spaces, which is to limit the in-flight to be less than twice the measured path bandwidth delay product. And notice this does not use the word C-wind. The algorithm doesn't actually have a C-wind in it. This logic happens directly. In some sense, you could compare the bandwidth delay product as to an estimate of C-wind, but it's not really the same thing. So how does this look in reality? Next slide, please. If I have an optimal operating point, and I want to find it, and I'm going to walk towards it. Next slide. During slow start, BBR, like other TCPs, doubles its rate on every ACK. It actually does this continuously. So this graph here shows round trips, but in fact, the rate varies continuously because each ACK coming back after the initial window updates my estimate of the round trip of the data rate, which is a little bit higher than the previous ACK. So there's this sort of a smooth differential equation, slow start. And at some point, the data rate stops rising because I fill the network. And here again, I'm showing 1 point per round. The 3 points on the right, I got back the same bandwidth estimate, and that's a clue that I've filled the network. This turns out to be a very robust estimator of when to exit slow start. Next slide. So after I've exited from slow start, I then adjust the window downwards, actually do the inverse multiplier to come back to that operating point. And I know exactly where it is at that point, because early in the slow start, I got good measures around trip time, and late in the slow start, I got good measures of bandwidth. So I can come directly to the right operating point. Next slide. And then in steady state, I did their back and forth between the current parameters are exactly operating at exactly the optimal point and 25% above it. And I do that to probe the bandwidth, and I do that sort of consistently. Next slide. And once every 10 seconds, if I haven't seen a new minimum, I cause the minimum by essentially pausing the data. I drop to a low rate. Again, the details there have drifted slightly, but one of the key aspects is everybody uses the same interval timer, the same 10 seconds timer. And so the flows tend to self-synchronize, so everybody measures the minimum RTT at the same time. And this is actually important because it's how BBR gets fairness, because you make sure that everybody sees the same minimum RTT. Otherwise, one flow is likely to see a different flow standing queue. And that completely prevents you from being able to do any sort of fairness calculation. So it's deliberate that this measurement interval implicitly synchronizes across flows. So how does it look in the field? First of all, BBR can fully fill a link in spite of pretty high packet loss. This was a slightly earlier version of BBR. I don't think the numbers have changed significantly. It runs just fine out to 15% loss. Oops, I'm sorry, next slide. I forgot to say that. Next 2 slides. Yes. BBR runs just fine out to about 15% loss, and then it has a cliff. There's some details on how the recovery works and so on that determines exactly where that cliff is, but you can run at 1% or 0.1% loss, and it will easily fill a network. One thing you will notice about this is that at extremely low loss rates, Cubic actually outperforms BBR. This is because BBR deliberately gives up about 2% of the bandwidth in order to do the minimum RTT measurements. And that 2% of the bandwidth is actually an engineering parameter. You could make it 1% or you could make it 0.5%. But the smaller you make it, the more risk you are at of having the entire system fall into divergent behavior where everybody is measuring everybody else's standing queue, and it ratchets up the standing queue. And the explosion, if you get into that region, is a system-wide slow start to max queues everywhere. It's not a good behavior, and so throwing away 2% of the network to avoid that behavior is a good idea. And anybody who says they can beat that 2%, well, we could turn the numbers. We'll beat the 2%, but then we'll sleep less well at night. Next slide, please. BBR also does really, really well on overbuffered networks. This is an example of a network where the buffer size is adjusted, and BBR basically keeps the standing queue that's very, very small, well, Cubic is controlling against queue full, so as the queue gets bigger, you have more and more problems. I saw a question about how it behaves against Cubic. I will talk about that later. It's an interesting story. I will get into it, and it's not a straightforward answer. Let's see, next question, or next slide. I'm sorry. So if you look at MultiFlow Convergence, BBR actually does pretty well at the particular choice of bandwidths here, which is 100 megabit link. I don't remember off the top of my head, but I believe that Reno and Cubic do something vaguely similar timescales. This looks good, but not profoundly good. Where it looks profoundly good is if I run this 10 times faster or 100 times faster, both Reno and Cubic become orders of magnitude more sluggish. They'll take hundreds of seconds or thousands of seconds to converge. BBR, the convergence time, is independent of the bandwidth. It's actually a really, really important result, and it's one of the things that I talked about before I came to Google was what do you need in a congestion control in order to make it scale with bandwidth? And BBR actually has a bunch of those properties. Basically, the control time does not scale with data rate. The control time does scale with round trip time, but it does not scale with data rate. And BBR is the first seriously fielded congestion control that has that property. And what that means is, this is the diagram for 100 megabit. It could just as easily be 100 gigabits, and it would look something similar. And that is profoundly advantage. What you see also in this little notches at 30 and 40, those are the minimum RTT measurements, and they all come into sync. And the fairness doesn't really converge until those timers become synchronized, and then it converges very well. You can't even see the notches in the individual flows for where they do the measurements, but they're there. Next slide. So startup behavior. First of all, there's one. This is showing time sequence plots of cubic and BBR. Hopefully most of you are familiar with that. What's key about this is that BBR here at 3/4 of a second is back down to a small q, and cubic is still growing a q after it's switched to linear in-flight growth. Because both BBR and cubic fill the length, the ACK lines for both of these are essentially the same. And so the forward progress in this case between BBR and cubic is identical. The performance is identical. There's a tiny bit of difference in the arrival in the first few round trips, but once the link fills up, those lines are the same. And because of the shape of slow start, they match. The BBR slow start was made to match cubic slow start, actually. So this is the behavior on startup. You can see that the spacing between the green line and the blue line is the queue depth. BBR ran it up to a good size queue, and then after a couple of round trips said, I'm running too fast, and then it reduced the queue. The spacing between the green line and the blue line is one delay bandwidth product during the steady state, and you can see that the BBR periodically is probing upward to see if it can go faster, and it doesn't make the ACKs faster. It doesn't help. Next slide. Okay, this is one picture of one data point was taken on Neil Cardwell's personal cell phone. He's the person who wrote most of this code in Manhattan, comparing BBR to cubic. And it makes the observation that BBR's more accurate, that sensing the plateau in the data rate is a more accurate way to detect the end of the slow start. And cubic tends to come out of slow start early, either because of jitter in the delay, which is what probably got it here on the LTE, or because of a small number of packet losses early in the connection. And BBR just does a slow start up until the bandwidth plateaus, and it's running at full speed. So this is one data point. Wouldn't call this a study, but next slide. The telcos are really interested in it because it turns out that BBR does effectively twice the performance for short transactions on LTE because of this effect. And this is real data. I actually don't know which carrier it's from. The person who sent them the message to the data to the BBR list used a Gmail address to send the message, so they did not admit who they were working for. I'm sure somebody else can find it, but it's still kind of a profound result that it's effectively twice as fast as cubic for transaction sizes up to some fairly large size. I actually don't remember where it tops out, but anyhow, that's great. So next slide. So BBR is already deployed at Google, not quite everywhere, but it makes a huge difference to us. If you're using Google Search, if you're using Google services, you're running BBR. It makes a big difference to the user perceived quality for YouTube. It makes searches faster. I don't know that you can see 2%. 12% longer mean time between read buffers is actually a big deal because it greatly affects the quality of user experience. And it does not, much the 32% lower RTT value, remember that's across a very large number of users, gives an indication of how much it improves browsing while watching video, because the browsing is very sensitive to the queuing delay caused by YouTube video if you're rate constrained. It does, however, increase the loss rate, and we'll talk a little bit more about that later. So next slide. Okay, so we had some interesting adventures, and I was not doing the work, but I had sort of a front row in a lot of this, and various things that cause problems. One of them is LTE has a couple of different modes that it switches between. It needs backlog in order to trigger the mode switching, and the 25% bandwidth probing is actually because that was the smallest amount of bandwidth probing that would reliably cause LTE to change rates. This is sort of a co-design parameter that also means that the minimum amount of jitter that BBR is going to introduce to real-time traffic on a parallel path is 25% of the delay bandwidth product of the path. There are all sorts of people who would say, oh, we should make use of BBR. We should do things to reduce the Q jitter introduced in the network. But if introducing that Q jitter means that we can't trigger mode shifting in LTE, it doesn't work for us. And so there's actually a sort of a global design parameter, which is how much Q jitter is the correct amount of Q jitter. And there's a trade-off, a global system-wide trade-off on how they fit together. The other thing that we ran into is that delay alone is a really noisy signal. Part of the reason why Cubic has troubles with LTE is because the ACK channel is slotted. There's an explicit scheduling mechanism for when the ACKs come back. And if you arrive at if an ACK arrives at the queue for a long time, it will wait. And the queuing delay or the queue release time is quantized in time. And so the scheduling mechanism introduces a huge amount of jitter, which is often as big as the round trip time on some paths. It could be huge. We had a lot of problems with ACK decimation of various sorts. This is generally touted as an optimization, but people who tout it as an optimization don't understand that TCP is actually measuring every ACK, or in principle is measuring every ACK. And when you decimate the ACKs, the sender has less idea about what's going on and is flying blind. We had a lot of problems with token bucket policers. BBR very, very quickly discovered the unshaped, the raw rate of the policer, the raw rate of the link. And then the policer said, oh, no, I was lying to you. You can't really go 10 megabits or 10 gigabits. You've only got a 2 megabit service. We're cutting you off at 2 megabits. After TCP is streaming at full link rate. And this causes massive packet drops in some parts of the world, and it wastes capacity in parts of the world precisely where capacity is most expensive. There are a couple papers we published about that. A couple papers that various people have published about that. The things that certain companies call shapers are really policers, and they're really pretty evil. And then finally, the metal boxes as I refer to them, that tamper with things and get in your way, and they think they're helping and they're not. So, okay, enough about that. Next slide. So there were also lots of adventures in doing the sort of the development process. And as part of this has to do with a lot of this happened, well, there's an awful lot of lore which is not documented in RFCs, and perhaps this is a bug of the internet, but the ultimate standardization force in the internet is you have to interoperate with all of your competitors. And no matter what the RFC says, if you build it the way the RFC says and it doesn't work on the net, it doesn't count. You got to build it the way that works on the net. And there was a lot of learning about all the real things out of the network that don't match the standards. And the other thing is that because of the way the instrumentation works on measuring the maximum bandwidth and the minimum RTT, they need to put actually a huge amount of state in essentially the retransmission queue to carry all this information and do all the measurements necessary to do things to get it to work. I'm actually going a lot faster than I should be, so I should be talking. Okay, next slide. I'm going to talk about some things that aren't working. Next slide, yes. So if you look at all of the things that BBR does, there's some sort of obvious high-level abstract ways in which we could do it better. It doesn't do well with small queues, and one of the consequences of the way BBR controls is it actually causes more loss than it maybe than we would prefer, and that makes it under some certain circumstances not behave fairly with Reno or Cubic. And it would be really great to find a way of reducing the RTT and loss rates for bulk flows under certain conditions where you detected various problems. Conflicting with that, because it's sort of in the opposite direction, for Wi-Fi and cellular and DOCSIS, which have slotted schedulers and mode shifting driven by backlog, there's a minimum amount of backlog that BBR needs to push into the network, which is often bigger than the maximum queue tolerated from the previous bullet. And so there's a conflicting requirement that we do want to create standing queues under certain environments to help these environments with their scheduling problems. Wi-Fi wants to batch data, it wants to have bursts of packets, which means that you need to inflate the window size by the optimal bucket size for the Wi-Fi, a bunch of stuff like that. And the last sort of fundamental area is a 10-second pause. The measurement, the min RTT measurement actually costs you time. If you had a connection that happened to be 10 seconds in 1 millisecond, you might end up essentially waiting an extra RTT to get those last few packets through completely unnecessarily. And because of rounding in the code, there's actually a clamp on that it usually does a flight size of 4. I see the slide says C-wind. It shouldn't. But that's an issue. Anyhow, in principle, if we fix these problems or found the right balance, the right trade-offs on these problems, we would put BBR forward as a default congestion control for the internet. And there's a bunch of things we need to talk about, and we're tackling them. We're working on them at Google, and both inside and outside of Google, people are working on it. Next slide, please. So there are some more specific areas that that people have looked at or have been thinking about for BBR. Of course, the obvious one, which in this community, is fairness with other flows and what to do about it. A lot of this is based on the previous list. I should say, actually, these research opportunities are drawn from multiple talks, so there's some overlap in them. The current work is actually focusing on the shallow buffer case and dealing with cross traffic and making that part of the behavior better. One of the things we're looking at doing is I didn't mention TSO. So TSO causes a problem in that every packet in the TSO, except for the last one, except for the first one, is queued by the TSO itself. The TSO is where you use the NIC you send essentially super packets down to the NIC, and the NIC chops them up. The first one is the only one that's got an accurate measurement on the TSO, but if you look at, for instance, delayed ACK, if it sees a packet coming down the wire, it knows that there's going to be another one suing it. So it almost never acts the first packet in the TSO first. And so the TSO optimization at one end and the delayed ACK optimization at the other end sort of fight against each other, such that you never actually see the minimum RTT. And this is a subject of, there's a lot of work going on to try and accurately understand and model the jitter introduced by both TSO and delayed ACK and any ACK thinning that's going on. To I'll put it this way, this isn't the language, that isn't really the right language, is to sort of estimate when ACKs should have arrived on the basis of when they did arrive and how we think they were delayed. So I'm not going to go into detail on these. Next slide. So we're looking for more data, and we love PCAPs. And if you find anything that you think ought to work, and it doesn't work, and it does odd things, people who are experimenting with it, and I know there are people in this community who are experimenting with it, send PCAPs. I will, at the end of the slide, I have a mailing list pointer. I want to point out that there's some issues in the HPC environment, which is where I cut my teeth. I actually spent, for those of you who don't know me, nearly 30 years at Pittsburgh Supercomputing Center doing HPC kinds of issues before I came to Google. And I'm going to talk about the HPC specific issues on the next slide. So, next slide. So, there are two things that are sort of unique about the HPC environment, which are not common in Google at all. One is end-to-end paths for which there are many bottlenecks that are the same interface rate, the same. I'm suspecting that you are mostly 10 gigabits, where there are multiple 10 gigabit bottlenecks, and the potential for the bottleneck to move from one queue to another, for instance. The potential, and there's a whole bunch of dynamics that can come from this kind of system, which are not ever visible in our systems. And the other thing that is much more common in universities and HPC environment is aggregation at small to intermediate levels. University campuses, there's probably more than 10 flows. I don't know how wide you guys are striping flows now for big data transfers, but there's actually a bunch of dynamic issues which are different at, say, 3 flows than at, vastly different between 3 flows and 1 flow, and different between 3 flows and 3,000 flows. We do test at global scale, but only for a certain subset of the common cases. Most of their transfers to the users have a bottleneck near the user, which is generally substantially overbuffered, and it behaves like the long queue case. And most of the flows inside of Google are very, very, very high aggregation. And these two cases are a lot easier in many ways than the small aggregation case, which we tested small aggregation, but we can't test a small aggregation better than the typical university can test it a small aggregation. You know, you run an experiment in a lab with a little cluster and say, oh yeah, we've got some data points. For these two cases, we can get 1 million data points in a day. For those two cases, it's much, much smaller than that. 1 million data points is underestimating. Next slide, please. So it's time to revisit loss-based congestion control. That's how the internet ran for a long, long time, but it doesn't scale anymore to the current internet. It's either too late or too noisy, depending on details of the path. Bbr does much better because it uses direct observation of bandwidth and RTT and has sort of an explicit model of the network. we're using it. If you've looked at our papers on our network, we're running it on V4, and it works better for us in nearly every parameter except slightly higher loss rates. It's running in quick for people who are using the new transport under Chrome and our servers. You're often using it when you don't know it. If you run Chrome on your PCs or laptops, look to see for UDP traffic. And we know that we regularly consult with the FreeBSD folks at Netflix who are looking at it to them, because the same improvements that apply to us apply to them. So, and we're actively working on applying the algorithm. Next slide, which is my last slide, and I'm actually early, aren't I? Yeah, a little bit early. There is a Google Groups forum on BBR Dev. Just search Google Groups BBR Dev, and you can join it. And there's lots of conversation there about experiments that people have done and sharing of results. And if you say, I got this weird result, the immediate response you will get will be, please send a PCAP. So with that, I'll turn it over to questions. Oh, I wanted to go on to one more thing. 2 slides after the backup slides. So this is a comparison between BBR and Cubic for one flow as you vary the buffer size. And I wanted to put together a little mini talk on this case. It's actually a rather interesting problem. And there's all sorts of hand-wringing about it, but I realized that it's actually pathological to run a network with less than a delay bandwidth product worth of buffering. Although it's very common because buffering is so expensive, in a fairly fundamental way, it doesn't work. And the real issue is that BBR and Cubic both fail in that environment, and they fail in different ways. It's sort of an anomaly that if I have a single BBR flow and a short queue bottleneck, BBR can get essentially 100% utilization on that flow. The reason this is an anomaly is because the time it takes, the control system by itself isn't sufficiently stable, because the control gain, that is the, I should be trying to do this without slides because I couldn't figure out how to diagram it, but the problem is if the queue is too short, an error in the signal is integrated for full round trip time will always exceed the size of the queue. And so if I pick the wrong data rate, by the time I get back any signal, I've potentially overrun the queue by a whole delay bandwidth product worth of data. And the problem is that Cubic and other loss-based congestion controls, since they can control up against the onset of the cliff, they end up setting their average rate to well below the knee. And since Cubic has a way of sort of directly observing the knee, it tends to set its data rate, its hunting noise tends to be above the knee. So one of them, the loss-based set below the cliff, and BBR sets it above the knee. And in that case, BBR very much outperforms Cubic. And BBR, the way it does this is it causes a lot of loss rate for Cubic, which it's okay with, and Cubic can't stand. On the other hand, if you're way over buffered, Cubic beats BBR. However, there's actually a funny result here. The difference between Cubic and BBR turns out to be smaller than the difference between Cubic and pure Reno. And actually, BBR versus Cubic does better than BBR than Reno versus Cubic, which is sort of a surprise result. So one definition of how fair does it have to be is it meets the bar that is no less unfair than the current protocols and the current protocol mix. So, are there other questions? I did not arrange to have them handy.
So thanks, Matt. This is Eli. I have one. So you talked about you said that there were some things that this community could do to contribute to the testing that needs to be done. Could you go into a little bit more detail about the kinds of things that would be useful for us to be looking for or setting up?
So I'll turn that around in kind of a different way. My intuition is that there is a potential for there to be surprises in the I'll say small integer aggregation case that are things that we didn't anticipate. So I have a pretty good mental model how a lot of these things work, and I do a lot of my work actually by imagining thought experiments. And if I build a certain pathological network, it will behave this way. And if you build a simple enough network, you can intuit what the behavior is and nearly always get it right. And it tells you about sort of a corner of the design space, the operating space. But I have a feeling that there's some things that will go on at moderate aggregation that are completely out of my imagination, and I don't know what they are, so I don't know what to look for. The issue there is that we're not at a profound advantage for testing that environment. I mean, Google does have a profound advantage for testing in certain other kinds of environments. Our end user case and in our fabric or WAN, internal WAN case, we get real-time statistics on lots and lots and lots of flows, and so we have a great deal of confidence in our answers. But running 10 flows and running 10 flows across campus on real gear is not something that we do ever.
Right. Okay.
And so anything there that happens that is sort of not something that you would intuit is something that should be looked at.
Okay, I can think of a couple of things. So for like a lot of the data transfer nodes that our community is running now are using Globus as their sort of default tool, right? And so Globus is sort of small scale parallel in the general case.
So what are the things I didn't know? Globus was coming on as I was leaving PSC, actually a little before that, and I didn't know what the typical widths were.
So so the default is, I think, so it depends on what type of thing you're doing. If it's your laptop, it's not parallel. But then it's like 2 to 4 unless you start turning the knobs, I think. But they have two knobs, right? One is concurrency and one is parallelism. So the concurrency is how many processes are used for a given larger transfer. Right, and then parallelism is the number of individual flows per concurrent process.
Right.
And so from the perspective of a given host, you can get somewhere between sort of 4 and 32 streams fairly easily.
Okay. Can you dial it below that?
Below one could, yeah, it tends to perform less well for a couple of reasons that I at least haven't fully quantified, but I suspect it's either per file performance on like parallel file systems or per mount point performance on parallel file systems. Because the other thing that they're doing is aggregating a set of DTNs into one named endpoint. Okay, and the transfer occurs between named endpoints, which means I can mux it across multiple Linux boxes, and then there's a set of processes that run on set of processes with parallel streams per Linux box, right? And so if per mount point performance is your problem, scaling the number of DTNs helps you. If per file performance is the problem, then you want to be writing multiple files simultaneously. And I at least have not fully characterized that space yet.
Right. You might try it with SSD.
Right. And none of the, so for individual sort of fat servers, we've seen SSD boxes there. We have not seen significant SSD for like, front-ending Lustre, GPFS or something like that.
Right.
We're working with NERSC on their burst buffer, which is SSD. They've got a significant fraction of a petabyte of flash on that thing. But it's not exposed yet in a way that we can use it.
Yeah, you might find that single stream BBR does better than even 4 streams. It really hurts BBR to try to jockey. There's a bunch of sort of fundamental reasons for it. Basically, the model that it gets for the round trip time and min RTT is exactly correct if there's a single flow during the measurement. But if there are multiple flows during the measurement, it naturally converges actually against the secondary control. And if you don't have a full delay bandwidth product worth of buffering, it ends up running at a fairly high loss rate and working the recovery machinery hard. And you end up with 4 control systems and 5 state variables. One of them being the Q depth.
Right.
Well, I should say one intrinsic physics function, 4 control systems trying to pick rates, and 5 state machines, which are the 5 state variables, which are the 5 rates that you're picking, and the Q depth. And the dynamics of that system, funny thing, is more complicated than 2 estimators and 1 state variable. And so the BBR, if it's not sharing the link, just nails it. It'll run 100% utilization, well, 98% utilization. Absolutely clean, but it's sort of not supposed to work at that scale because it doesn't. This is the Star Wars dropping the bomb in the little tiny hole problem. You don't actually have enough time to get the noise small enough to hit it into the hole. If you didn't have, if there were any noise in the system at all, and it works because there's no noise.
Okay. So we have some questions from other folks here, so I'm going to stop monopolizing the space. So has any work been done towards characterizing the traffic that results from BBR with regard to self-similarity, right? So is BBR self-similar?
So I don't know that it has actually been studied as a self-similarity problem. Van has probably thought about that issue. When we run BBR inside of Google, it's muxed against itself very heavily, and we know pretty well how it behaves in that environment. I have to be careful because I don't know the state of deployment. The way we control it, we actually do a flip per flow to turn it on, and so we can decide in real time if a given flow, if we're just going to leave it cubic or we're going to change it, and we know. Certain applications are not authorized to use it. Most applications use it all the time. To some extent, it depends on how far away you're going. There's a bunch of criteria like that, and it just and they watch it. They watch the loss rates. They watch the link utilizations. They watch everything. So.
Okay. Have you tested BBR with jumbo frames?
So I saw that question go by. Let me give an outside of Google answer to that question. So jumbo frames is the only thing that I worked on in my career that really hasn't happened, and I was very, very careful when I came to Google, even before Google, although I suspect it had in some sense failed, to not actually call the question. It's like, okay, we really want to run jumbograms on Ethernet everywhere, but this darn IEEE is getting in the way. I've since realized that there was a sort of a flaw in my understanding of the problem, and I think jumbo frames are doomed in a kind of a subtle way, and that is that the real MTU limit on almost all these networking technologies, there's 2 different limits. One of them comes from a counter, which is easy to set. I can change the register someplace in the device if it supports it. The other is implicit in the design, having to do with things like clock stability. and thermal stability and a bunch of stuff like that. Some designs are synchronous and don't care about such things, and some designs are not. But the second problem is really an analog parametric issue. And there's no way for the digital part of the system to know what assumptions are in the analog part of the system.
Right.
And so MTU probing, in fact, doesn't work. And one of the things that sort of scared me is near the end of my time at PSC is we had a GBIC that was unfortunately an alpha test from a vendor, and they wanted it back because I would have liked to have done it that ran error-free at 1500 bytes and 1% error at 4K.
Right. I saw something similar to that once too, actually.
And in fact, it was in spec.
Yes.
And path MTU, the packetization layer path MTU discovery that I spent a year on the RFC to do improved MTU discovery can't fix the problem because 99% delivery looks at it like it's completely clean. And one could imagine a change of heart in the IEEE where they say, okay, for synchronous devices, we'll define a definition for what a jumbogram is. But they've actually very scrupulously avoided making it such that anybody can actually make a certification claim for anything more than what they call jumbo, which is 16, 18, or whatever. I forgot what the number is, but it's it's a tiny bit. It's basically extra headers. They made it such that you can't actually write a requirement spec. They've been very careful about making sure you can't write a requirement spec, which gives a rigorous test that'll prove interoperability between two people who claim to be jumbo capable. So, and so at a place like Google, we have much better control of the hardware. We know exactly what it does. We have people who can actually look at the designs and say, okay, let's redo the math in this calculation and see what the clock stability matters, or say, oh, it doesn't matter because we're actually synchronous, or it doesn't matter because whatever reason. And one of the things that I didn't realize, for instance, is that I guess this is not true above. Well, for 100 megabit Ethernet and below, for sure, the phase lock loop is actually only phase acquisition. It's not frequency acquisition. And so the phase of the last bit is entirely determined by clock stability. And you can't win. You can't beat that. And part of the reason why the Ethernet is so cheap is because it is so simple. And it's plug and play. And Jumbo flies in the face of a lot of the design principles behind it. So I never call the question on Jumbo, but I think Jumbo is dead unless you actually own all of the gear on the path and can review the engineering on it.
Okay. Or
test the daylights out of it. And testing the daylights out of it includes thermal, full thermal and power supply margin testing. It might be that it works fine when the air conditioning's doing great, and it fails when the air conditioning's off. You're running 10 degrees warmer. Who knows? Next question.
Next question is B4 running on small buffer switches, and how does that square with the buffer size and bandwidth delay products?
So yes, B4 is running on a variety of gear. I actually don't know that much about a lot of the hardware. They are not deep buffers. The big difference is that B4 is actually, there's a paper, I have to think carefully because I don't, there's a B4 is admission controlled. And it's actually admission controlled in fairly small increments. And the admission control system on B4 keeps it out of trouble. And that's basically the short answer.
Right. Yeah. I mean, if you shape at the edges, there's a lot of stuff you can do, right? That
Yep.
fixes a lot of problems.
Right. Exactly. And admission control does that. And there's actually, since the transactions are also small, there's no reason to have any flows that are going at that kind of at even gigabit speeds. I mean, most of them are, okay, here's 100 packets and you're done.
Right.
It's like, it's a transaction. It's not a flow. It's a transaction.
Right. So yeah, you're dealing with fundamentally different dynamics.
Right. So for instance, the BBR that was deployed internally didn't even do the minimum RTT measurement because there were no flows that were long enough to hit 10 seconds at equal bandwidth. Not no flows, but it wasn't an issue. There's enough flows that since nearly all the flows finish in less than 10 seconds, everybody gets good round trip minimum RTT measurements anyhow, so you don't need to do the explicit measurements.
All right. I have one last question. And this goes back to what we were talking about parallel streams versus single streams.
Mm-hmm.
One thing I'm confused about is, so you're talking about if one process has 4 parallel stream or 1 single stream, right? And you would say that doing a single BBR flow would do better than 4 BBR flows in that case.
Yep.
But my guess is that in a server environment, you're going to have one box, right, that is serving multiple clients at the same time. So from the perspective of the kernel on that host, don't you have the same problem? What am I missing?
So if you're talking about what we refer to as our edge, so we're serving to customers.
Right, so outgoing YouTube or something, right?
All of those customers have their own independent bottlenecks. And so BBR is measuring the bottleneck for each customer independently. And I do admission control to make sure that I never cause congestion on my own egress interface.
So the issue then, let me repeat this back and make sure I understand. So the issue is when you have multiple connections that are measuring exactly the same path, and
right.
therefore getting incorrect measurements because
right.
they can't see
because they're dueling with each other, and right. And that situation is worse. That situation is better if the host interfaces are slower than the core. So the combination of end-to-end uniform bandwidth, and I don't know if how much you guys have just deployed 40 gigabits yet, but
fair amount.
When I left, everything was 10. When I left PSC, 10 gigabits was pretty common, but it was end-to-end 10 gigabits at multiple places. And then what happens is I don't have any smoothing by the host interface. I guess I'm assuming you're running 10 on the host and 40 on the WAN, but if you're running 40 end-to-end, you have the same problem. And if you have a bottleneck in the middle, which is sometimes running an intermittent 40 gigabit flow from a different pair of hosts, they're sharing a bottleneck, and there's all sorts of dueling that's going to go on there, and the signal to noise ratio, exactly half of the total signal is my own, and half of the total signal is somebody else's noise. So the signal to noise ratio is 1-to-1 in that environment. And
that's not awesome.
It's a tough environment, and like I said, we don't have that environment happen anywhere.
Right. Okay. So we have a test bed that where we can probably model that.
Right. I should say we can make it in a test bed, but we're doing the same experiments as you're doing, and it doesn't make any difference to our customers, and so they're not a high priority. Because we can run things in clusters and stuff like that. But what we do care about is, okay, I just did a flag flip in Asia or in some country, and I changed a bunch of traffic, and the numbers changed. Why? Do I understand why? Is it better? Does it hurt? Should I flip the flag back? All those kinds of questions, and because those matter. They matter to the users. They matter to the advertisers.
Right. Okay. Thanks.
So,
All right. Well, I haven't seen any other questions come in. If anybody has any last ones, speak now.
yeah.
All right. It sounds like we're good. Thank you so much, Matt. This has been
Thank
great.
you.
And
Yeah.
I'll send you a link to the recording as well if you want to retain a copy.
Sure.
And for people who are still on, next week we're going to have a talk from Globus. So maybe we can pepper them with some information about BBR as well. So have a good weekend, everybody, and we'll talk to
Yep.
you all soon.